In our last section, we talked about functions of more than one independent variable, and we also talked about how to graph them. In the next section, we want to focus on limits and continuity, basically following the path that we followed in Calculus 1. In Chapter 4, we'll only get up through derivatives. When we get into Chapter 5, we'll begin with integration of these functions of multiple variables. Now, when we're thinking about taking the limit of a function of more than one independent variable, it gets more complicated than it is in the one-dimensional case, where the domain is simply the real number line. There are aspects to both limits and continuity that occur when we have multivariable functions that don't occur when we have functions of a single variable. Let's think about an example. Here in the introduction, we talk about approaching a value of x from the left or the right. If we have f, which is a function of one independent variable, then we can take the limit as x approaches a, or the limit as x approaches a from the left, or the limit as x approaches a from the right, meaning that we have a number line. And if we have a number line, then x is getting close to the value of a somewhere on the number line, either by approaching from above or by approaching from below. There are only two ways to get to a, and that's from the left or from the right. This makes it much simpler in the single variable case. In the multi-dimensional case, let's just take this, well, the easiest one possible, which would be a function of two independent variables, adding one independent variable to the function. In that case, our domain is no longer a real number line. In that case, our domain is instead the XY plane. In this case, the question is, we're taking a value out of the domain, which will be an ordered pair, say XY, and we're asking, how can we approach some other value? In this case, it's going to be some other AB. How many different paths can you draw that will take XY over to AB? Yeah, unfortunately, infinitely many. So as the ordered pair XY gets close to the ordered pair AB, does the dependent variable approach a single finite real number? That's the question we need to ask. But in this case, we're not limited to a finite number of approaches as we were for a function of one variable. There are infinitely many paths that will take us from one point to another in the plane. This also has implications for continuity, because in continuity, remember that the definition is that the function exists at the point, or in this case, the ordered pair, and that the limit exists as the XY ordered pair approaches the ordered pair AB, and that they're equal to each other. So finding the limit affects the continuity. In this particular section, we have quite a few learning objectives, which you can see down here at the bottom. We want to be able to calculate the function, the limit of a function of two variables. We'll learn how a function of two variables can approach different values at a boundary point, depending on the path of approach. We'll have to define what we mean by a boundary point as opposed to an interior point. State the conditions for continuity of a function of two variables, verify the continuity of a function of two variables at a point, and calculate the limit of a function of three or more variables and verify the continuity of the function at a point in its domain. Let me share my screen with you and we'll get started. We're going to start with the limit of a function of two variables. Towards the end, we'll extend this to a function of three variables or perhaps more independent variables. Before we do that, though, we want to briefly review what is the formal limit formal definition of a limit of a function of one independent variable. Yes, we're back to that epsilon delta definition again. So the limit of a function of one variable, the formal definition, is to allow f of x be defined for all x values in an open interval, so round parentheses, containing the value a, which is coming from the domain, except possibly at a. In other words, it doesn't have to be defined at a, but it needs to be defined on some interval around a at all other points. Then let L be a real number. Then we write the limit as x approaches a of the function f of x equals L if for every epsilon that is greater than 0, there exists a number delta also greater than 0, such that if 0 is less than x minus a, the absolute value, which is less than delta, for all the x in the domain of f, then the absolute value of f of x minus L is less than epsilon. Okay, maybe in calculus 1, you never quite got what that definition was saying. So let's go over it. Let f of x be defined for all x in an open interval containing the value a, except possibly at a. Down here on the number line, we want to define some kind of interval around a. And notice that a is coming out of the domain. A is a value in the domain of the function, but it may not be defined there. So I guess in some ways it's not really in the domain, but it is an x value, right? So it may not be defined at a, but it's got to be defined at every other point in the open interval on both sides of a. So I've got to be able to get close to a from the right and close to a from the left. That's what the first sentence means. L is just a finite real number, 10,000, 42, -5, 1/2, any real number. Then we write the limit as x gets close to a, it never reaches a, it just gets arbitrarily close. How close? The next part is what specifies how close. For every epsilon greater than 0. Now, epsilon is chosen generally to be a very small number. What is epsilon? Let's take a look at the last line. And the absolute value, we have f as a function of x minus L. And this needs to be less than epsilon. Putting in an absolute value will force it to be non-negative. So really what we're getting is the distance between the function value at a point and L. Now, L is coming out of the range. So L is a y value. And epsilon is how far away from L we want to allow the function values to be. So the function value, f of x, can fall anywhere between L minus epsilon and L plus epsilon. And if that happens, it's only because we found a number delta. And this value of delta restricted how close to A you needed to be. So you have to have a positive distance. You can't be at A for the limit as x approaches A, but it has to be strictly positive. It's a distance. This distance delta says that as long as you're within delta distance of A on either side of A, but not at A, then the y value on the function, which is pictured here in blue, will fall between L minus epsilon and L plus epsilon. Notice that if you narrow the value of epsilon, you make a smaller value for epsilon, then the value for delta also gets smaller. You have to restrict it. It doesn't always end up being the same on both sides, But if, say, I could be 2 away on the left and 1/3 away on the right, I'm going to choose to be 1/3 away because that works on both sides. We always choose the smaller value for delta. And again, if you choose an even smaller epsilon, and you can still find a delta that guarantees that all the function values in the open interval around A fall within L minus epsilon and L plus epsilon, then you have proven that the limit as x approaches A of f of x equals L. Epsilon is totally arbitrary. It gets picked first. And depending on what you picked, you have to be able to find a delta that guarantees that the function values fall within this blue band. Now that we've reviewed what the limit of a function of one variable is, let's expand the limit definition. We're going to take a look at the definitions side by side. When we look at these here, we can see on the left column the definition for a limit of a function of one variable. And in the right column, in the blue font, we see the definition of a function of two independent variables, x, y. Let's see what's different. Let f of x be defined for all x in an open interval containing the value a, except possibly at a. On the right, we have let f as a function of x and y, so that's different, be defined for all points x comma y. So instead of a single real value as a domain value, we have an ordered pair in an open disk. Now, the reason why we're in a disk is because we're in the plane, the xy plane. So we're going to define basically a circle, right? So we have this circle centered at A to B, except it may possibly not be defined at that point A to B. Let L be a real number. That's the same on both. Then we write the limit as x approaches A of a function of one variable equals L. For the two variable case, we let L be a real number. That's the same. Then we write the limit as the ordered pair xy gets close to the ordered pair AB of the function of two variables x and y equals L. Very, very similar. If for every epsilon greater than 0, there exists a number delta greater than 0 such that that part is exactly the same on both. Epsilon is arbitrary but chosen first. If you pick an actual value for epsilon, can you find a delta that makes the next part true? Let's look at what the next part says. If 0 less than absolute value of x minus a less than delta, if the distance between the x value and a is positive and less than delta for all the x in the domain of f, then f of x minus L is less than epsilon. Over here, it says for all points xy in the domain of f in the open disk of radius delta centered at the point AB, except possibly at the point AB. Again, if you are close enough to it for all the function values in that interval on the left and in the disk on the right, then the limit exists, and the limit is L. In other words, if we have a function of two independent variables, x and y, so z equals a function of x and y, then the limit as some value xy approaches AB exists if there is some delta disk. Now, the scale on this particular graph is not 1-to-1, which is why this looks more like an ellipse instead of a disk, but it should be a round circle. So basically, the radius of this circle, and it is in fact a circle, it's just the scale is not 1 to 1. This is a circle of radius delta. If it is true that if I take any value that's inside that circle, x, y, and I take any path within that delta disk to get from xy to the point AB, and for all of those paths, those infinitely many paths, I come up with the same limiting value, and that is the limit of the function as xy approaches 2, 1. Now, the choice of delta depends on how close you want the z value, the dependent variable, to be to the limiting value. So we normally choose something like 0.01, 0.001. We want to be close, right? We don't want an approximation that's off by even 1. That's too far. If the limiting value is 4, I'd like to be between 3.999 and 4.001 or something of that nature. Once I've chosen that epsilon distance above and below 4, that sets the value of delta. It's a disk in the two-dimensional space because it extends in all directions from the point AB. All possible paths to get from this point, xy, right here, the blue dot, inside the delta disk, to the point what's labeled 2, 1 here. Let's now take a look at some various pathways. What do we actually mean when we say a ordered pair xy gets close to an ordered pair AB? What are we talking about when we say a path? Any curve that you can draw, and it does not have to be a function, anything that connects the point xy with the point AB but stays within the delta disk proves that the limit value is L. And you can see here that there are many different paths, and obviously I could draw infinitely many more. There are infinitely many paths that will take me from xy to AB. This is very, very different from the function of one variable. In that case, A is a point on the real number line, and you can come from the left or the right. That's 2 ways. That's it. In a function of 2 independent variables, there are infinitely many paths that we can follow. What does it look like when you draw this delta disk and project it into the surface produced by the function of 2 variables? Remember, a function of 2 variables will produce a surface in 3-dimensional space, which in this case looks sort of like a sheet blowing in the wind. The domain for the function is any ordered pair coming out of the xy plane that works inside the function. In this case, we have a delta disk surrounding the point AB. The value of delta is chosen depending on the value of epsilon for L. L is going to be between L minus epsilon and L plus epsilon. And that will project down how large the delta disk can be. All right. Let's go ahead now and talk about notation of the limit of a function of 2 variables. The notation that I prefer is ordered pair xy approaching ordered pair AB. That, after all, is what we're really doing. One ordered pair is following any curving path. Doesn't have to be a function, doesn't have to be smooth, though it helps, to get to point AB. It's also common to see it written the limit as x approaches A and y approaches B. But when you write it that way, you sort of lose the sense of what you're actually doing. You're taking a value, arbitrary value in a delta disk in the domain to approach a specific value. And you want to know, does the dependent variable, z in this case, approach some finite real number when you do that. Let's go ahead and talk about how we actually find the limit of a function of two variables. In Calculus 1, we actually learned to find the limit of a function of a single variable and practice it for multiple sections before we ever learned the epsilon delta formal definition. And you're going to find that it's pretty much the same for the limit of functions of two variables or three variables. We do have what are called some limit laws that will allow us to find the value of a limit more easily than using that epsilon delta definition. Let's take a look at these limit laws. We're going to let both f and g be functions of two independent variables, x and y. They'll be defined for all values of x, y, other than possibly AB, in a delta neighborhood, meaning a disk, around the point AB. So in space, AB has a little disk drawn around it, a circle of radius delta. And we're going to assume that this neighborhood is completely contained in the domain of the functions f and g. Also, we're going to let L and M be some finite real number such that the limit as xy approaches AB of the function f equals L, and the limit as xy approaches AB of the function g equals uppercase M. We're going to let C stand for a constant, a real number, a scalar. Then here are our limit laws. The limit of a constant is still a constant. This is the constant law that we saw in Calculus 1, and it applies in multidimensional space as well. Then we have what are called the identity laws. We had something very similar earlier in the case of a function of one variable. The limit as x approaches 2 of x is 2. We just substitute the value in. In this case, we split it into two parts because we have two independent variables. The limit as xy approaches AB of x is A, and the limit as xy approaches AB of y is B. What about the sum and difference laws? These work here just as they did in functions of a single variable. If you have two multivariable functions added together, then the limit of their sum is the sum of the limits. In other words, you can split it into two individual limits and then find the sum. Same for the difference, provided, of course, that the limit exists. You can only split it up if the limit exists. If the limit does not exist, then you cannot split it up before you find the limit. Now, there are a few more we need to go through. Let's take a look at the rest. If I have a constant multiplied by that function of multiple variables, it affects the limit value by multiplying it by a constant. This is exactly the same as what we saw in functions of one variable. What about the product rule? We also had a product rule in functions of one variable. Provided the limit of f exists and the limit of g exists, then the limit of their product is the product of their limits. You could split it into the limit of f multiplied by the limit of g. But again, to split it, they have to both exist. And exist means they're a finite real number. What about the quotient law? We had this too in Calculus 1. In this case, the limit of f has to exist, the limit of g has to exist, and the limit of g can't be 0. Thou shalt not divide by 0. If that's the case, you could split this into two limits. The limit of f as a function of x and y divided by the limit of g as a function of x and y. That gives us the ratio L divided by M, as long as M is not 0. The last two are actually related. They're power laws and root laws. We're going to split them into two cases. They're both powers, but roots are rational exponents, ratios of two integers. We're going to split the first part into powers that are the natural numbers, 0, 1, 2, 3, 4, 5, 6, 7. Really, we're interested in 2, 3, 4, 5, 6, 7. Let's suppose I want to find the limit of a function raised to a power. I know the limit of the function exists, but I don't know if the limit of the function, say, cubed exists. This limit law tells you that as long as the limit of the function exists, you can pull the limit inside the power, find the limiting value first, and then raise it to the power. So that would give us L to the third power, or L to whatever the power happened to be. We have a similar rule for rational exponents, but here we have to be more careful. Remember, for a rational exponent, the denominator determines the index of the radical. If the denominator is an odd number, it will accept positives, negatives, and 0. If the denominator in reduced form is an even number, it will accept 0 and positive numbers, but it will not accept negatives. In this case, again, we can draw the limit underneath the radical, provided that n is odd and positive, and for all L greater than 0, if n is even and positive. Note that this does not have a sign in front of the radical. So it's assuming for even radicals that it comes out to be positive, and that's why L is restricted to being non-negative. To find a limit, we're going to apply the limit laws to simplify the expression and sort of split apart the limit. If you find a finite real number, that is the value of the limit as the ordered pair xy approaches the ordered pair ab, then you're done. In practice, we're going to substitute the values in to see if the function exists there. This is part of continuity. Sometimes factoring and reducing will help as well, just as it did in Calculus 1. Let's take a look at the first example by simply plugging in the values and seeing if we get an answer. And then I'll go through the formal process of explaining why it works. So the first thing we're going to do is simply substitute in the values. So we're not actually computing the limit, we're actually substituting. So x is 5, y is a -2. Make sure you put them in parentheses so that you don't mess up the signs. Getting the wrong sign on something could change it from existing to not existing or vice versa. And that would be a major error. In this case, I have the cube root of 25 plus 4, which gives me 20, no, not plus 4, plus 2, 27, over 4 plus 5, 9, minus 1 is 8. When I take the cube root, I get 3 halves. I got a finite real number. That is, in fact, the limiting value. Now, what limit laws am I using to do this? So let's talk our way through this. First off, if I have an odd radical, I can pull the limit inside of the radical, provided I know the limit of what's inside exists. So the first step here is to take the existing value and pull it inside of the radical. Oops. So xy is approaching 5, -2, and all of this is under the cube root. Now, the next limit law that I would need to apply would be the quotient one. And the quotient one says, as long as both exist, are finite real numbers, and the denominator one's not 0, then you can split the limit between the numerator and denominator. So now I've got a cube root limit xy approaching 5, -2 of x squared minus y divided by the limit as xy approaches 5, -2, lost my parentheses, of y squared plus x minus 1. Right? Now we can apply the sum and difference laws to take the limit of each individual term. The ones that have powers, we can then pull the limit inside the power and apply the identity law. Let's write out one last step. So I've got this huge cube root. I've got the limit, and I'm just going to put squiggly marks for all of that at the bottom, of x squared minus, because I can pull the constant out, the limit of y divided by the limit as xy approaches 5, -2 of y squared plus the limit of xy is approaching 5, -2 of x minus the limit as xy approaches 5, -2 of 1. Now, the squared ones, we would apply the power rule, which says as long as it exists, I can pull the limit inside the power. Now, the limit of y is going to be -2. So in the numerator of this one, I'm going to get the following. The square of the limit of x minus -2. The identity law tells us it's -2. In the denominator, I get the square of the limit of y squared. I've got my square on the top one. The second term in the denominator just becomes the identity, which is 5. That's what x is. And the limit of the constant is the constant. The limit of x is 5. So I get 5 squared plus 2, which is 27, what we found above. And down here, the limit of y, the identity law, gives us -2, which squared is 4, plus 5 minus 1 is 8. So what we've done is we've applied the limit laws and we've evaluated the limit and we obtained the answer 3/2. Now, in practicality, you're probably not going to go through all these steps every time, as long as you understand that this is sort of the theory underlying what you do when you substitute. Now, what happens if you get something where the limit does not exist? In other words, you end up with something where the limit doesn't exist. Say you get an indeterminate 0/0 form. In Calculus 1, we dealt with these using L'Hopital's rule, but we can't apply L'Hopital's rule here. We have more than 2 ways to approach the ordered pair AB. So in this case, if we get some kind of indeterminate form, such as 0/0, instead of a finite real number like 3/2, then we have to think about the paths that we take to get from any xy in the delta disk to the point AB. It cannot be proven what the limit is using the paths approach, because there are infinitely many paths. Even if I checked 10 billion paths and all 10 billion paths gave me the value that the limit was 5, that proves nothing. Infinitely many means infinitely many. I would have to check all paths to prove the limit was 5, and that's impossible. What we can prove is if a limit does not exist. Because if I take 2 paths from xy to AB, and each path gives me a different finite real value, then I've found a counterexample, and the limit does not exist. So I can't use paths to prove it does exist, but I can use paths to prove it does not exist. Let's take a look at this approach. There are infinitely many paths to try. We saw that earlier in the picture. There are lots of ways to go from the ordered pair XY to the ordered pair AB. You just have to draw it without picking up your pen. However, from a practical standpoint, we tend to use the same kinds of functions over and over. And here are the functions we typically use. We'll start with the x-axis, which is the simple horizontal line y equals 0. Now, we can only apply this one provided that this goes through or the point xy. So if this line, this horizontal line, which is the x-axis, does not go through my point xy, then I can't use it, right? What about the y-axis? Or xy is really AB, right? What about the y-axis, x equals 0? This is a simple equation to test. It's a simple path, but the point I'm trying to get close to has to be on that. Then I can switch to x equals y if AB is the origin, all right, that'll work, or 1, 1, or 2, 2, or anything like that. Or I can shift it off center. If I want to use a linear function, I can simply center the line at the ordered pair AB to ensure it goes through that point. Notice that K is the slope of the line. Now, I could also use a parabola, y equals x squared, or y equals x squared plus 4. It just has to go through the point I'm interested in approaching, or y equal x cubed. These are listed in the order of difficulty in applying. The further down the list, the more difficult they become to apply. But again, this is not to prove the limit exists. You can't. There are too many paths to check. This is to prove a limit does not exist. Let's go ahead and take a look at an example. In this case, we want to find the limit as an arbitrary value xy in our delta disk approaches the ordered pair 2, 1. So whichever path we choose, 2, 1 has to be on it. Our function is the ratio of the quantity x minus 2 times quantity y minus 1, all divided by the quantity x minus 2 squared plus the quantity y minus 1 squared. Just as we did in the previous example, the first thing we do is substitute the value in and see if we get a finite real number. If we do, we are done. If we get an indeterminate form, we'll try the path method to see if we can prove the limit does not exist. There is no way for us to prove that the limit does exist, at least with the techniques and the skills that we have at this level. Let's go ahead and substitute the value in. So I'm going to put a question mark, and I'm going to replace x with 2 and y with 1. And I can already tell that I'm in trouble. You may be tempted to want to cancel some of these terms, but the addition in the denominator means that's not possible. The entire denominator forms one term, and either it all goes or none of it goes. In this case, I get 0 divided by 0, which is an indeterminate form. There's no factoring or canceling that I can do to simplify it, so I'm going to see if I can prove that it does not exist by checking paths. Now, normally, I would start with the x-axis, y equals 0, or the y-axis, x equals 0. But the point 2, 1 isn't on the x-axis or on the y-axis. It's also not on the curve y equals x, because the coordinates are different. So I'm going to use a generic curve that goes through 2, 1. Any curve that goes through 2, 1 will work. What I'm going to do is I'm going to try a line. I'm going to leave the slope here arbitrary. So let's see what difference that makes. I'm leaving my slope as m. What I want to do now is I want to substitute for that value by solving for y and substituting that expression into the relationship. In other words, I found a path to go from a point near 2, 1 directly to 2, 1 along a line of slope m that has 2, 1 as a point on the line. This is the point slope form of a line, which guarantees it goes through 2, 1. Taking the equation up here and solving this for y, I get that y is equal to m times x minus 2 plus 1, which if I want to multiply it out, gives me mx minus 2m plus 1. Let's go ahead and try substituting this in place of the limit. So I have x minus 2, and in place of y, I'm going to substitute mx minus 2m plus 1. And then I have minus 2, minus 1, right? And then in the denominator, I have x minus 2 quantity squared plus, replacing y with mx minus 2m plus 1 again, and then minus 1 quantity squared. Now I need to simplify this and see what happens to the result. Another option is simply to choose values for m. Choose 2, choose 1. You can't choose 0 because that would not give you a line going through 2, 1. You could choose any non-zero value that you wanted. Let's go ahead and multiply these out and see what we come up with. In this particular case, we're going to get, well, first thing I should do is add 1, subtract 1. So I can simplify this a little bit by saying I have the limit as xy approaches 2, 1, and I'm going along a linear path. So I have x minus 2, does not cancel in the denominator, and I end up with mx minus 2m since the plus 1 minus 1 cancels. In the denominator, I have x minus 2 squared plus, and then I'm going to have mx minus 2m quantity squared. Okay, so I have that. All right, is there anything I can do with this? What's the next thing that I can do? Well, the next thing that I want to do is maybe take out that m that I've got in the denominator. I've got an mx minus 2m and it's being squared. So if I want to, I could rewrite this as m times x minus 2 quantity squared. That means both the m is being squared and the x minus 2 is being squared. So another way to write this is m squared x minus 2 quantity squared. Aha! I hope you can see now where I'm going. What I now have for this limit, and I'm going to go ahead and write it out the long way to make sure that I don't lose anybody, is x minus 2, and I'm going to factor the m out of the numerator 1, times m times another x minus 2. And in the denominator, I have x minus 2 squared plus m squared times x minus 2 squared. I still have 2 terms in the denominator, but they have a common factor now, which is x minus 2 quantity squared. And the numerator also gives me an x minus 2 quantity squared. So the next thing I'm going to do is simplify it. X minus 2 squared times m in the numerator If I factor out the common factor, I get x minus 2 squared times 1 plus m squared. Now, at this point, all the addition and subtraction is buried inside parentheses, so I can reduce factors. It consists of nothing but factors and divisors. So the x minus 2 quantity squareds cancel. Aha! And this gives me the limit as xy approaches 2, 1 of the expression m divided by 1 plus m squared. Now remember that in this limit, it's dependent on the value of x approaching 2 and y approaching 1. M isn't in there, which means the answer depends on what I choose for m. Let's say that I were to choose the line where I had y minus 1 equals 1 times x minus 2. This could be option 1. In this case, m equals 1. In that case, my limit would give me 1/2. What about option 2? Let's choose a different m. Suppose I chose y minus 1 equals 2 times x minus 2. Both of those lines go through the ordered pair 2, 1, but they take a different path. In this case, my m equals 2, and my limit value would be 2 divided by 5. 2 divided by 5 is not 1 divided by 2. What I've proven is that these two paths have different limiting values. And because these two paths have different limiting values, the limit does not exist. And that's what we've proven. Let's now take a look at the next example. This is the limit as the ordered pair xy in the domain approaches the origin. The function is x squared y squared divided by the quantity x to the 4th plus 3y to the 4th. The first step you should take is to try to replace the x with the x coordinate and y with the y coordinate to see if you get a finite real value. In this case, you get the indeterminate 0 divided by 0. Again, we won't be able to prove that the limit does exist, but let's take at least a couple of paths and see if we can prove it does not exist. In this case, we need to find a function that goes through the origin. In fact, we need at least 2. All of the ones that I suggested earlier will work here. The x-axis goes through the origin, so you can use y equals 0. The y-axis, x equals 0, goes through the origin, so you can use it. The line y equal x also goes through the origin, so it's a good choice. So does the parabola, y equals x squared, or the cubic, y equals x cubed. All of those functions go through the origin. Choose whichever 2 you like, and let's see what value we get for the limit when we take a different path to get from arbitrary xy to the ordered pair 0, 0. In this case, we're going to start with the x-axis and the y-axis since they're usually the easiest. The x-axis is y equals 0. The y-axis is x equals 0. If we're approaching along the x-axis and we're getting close to the origin, the y value has to be 0 because we're on the x-axis. All of those values are x comma 0. So if we're on the x-axis, the x changes value, but y equals 0. So we're going to substitute 0 for y, but we're going to leave the x alone. When I substitute that in here, if I take it along the x-axis, which of course is y equals 0, this leads to the following path evaluation. And I lost my arrow. There we go. I still have x squared, but the y gets replaced with 0. In the denominator, I still have x to the 4th, but again, y gets replaced with 0 because on the x-axis, the value of y is always 0. In this case, this is going to give me the expression that 0 is divided by x to the 4th. Again, this is a limit. So I'm approaching the origin. X is approaching 0, but it never actually gets there. So 0 divided by a non-zero value is going to give me 0. The limit as xy approaches the origin, moving along the x-axis, gives me a limiting value of 0. Let's see what it does when I approach along the y-axis when x equals 0. In this case, if I'm approaching along the y-axis, then x equals 0, but y changes value. So this is going to lead us to the limit where we substitute 0 for x, but leave the y alone, sort of the opposite of what we had last time. So we have 0 squared times y squared divided by 0 to the 4th plus 3y squared. This is going to give me 0 in the numerator and y squared in the denominator. But again, this is a limit. Y never actually gets to 0. So this is defined and it becomes 0. So far on these two paths, they both give me 0. Let's see what happens on a third path. This time, let's use the line x equal to y. It also goes through the origin. Again, the fact that two of them gave me the same value means nothing. There are billions and billions of paths to check. You can never prove it exists by checking paths. You can only prove it doesn't exist. This time, we're going to use the path x equal y. If you use the path x equal y, then you're going to substitute y in place of x or x in place of y. It doesn't matter which one, just get it written in terms of one variable. So this is going to lead to the following limit, where we are going to replace the y values with x. So I have x squared times x squared, since both x and y are equal, divided by x to the 4th plus 3x to the 4th. Now in the numerator, this is going to give me x to the 4th, and in the denominator, this gives me 4x to the 4th. But the x to the 4th cancel, and that leaves me with the value of 1/4 for the limit along this path. This path does not match the limiting value of the previous two paths. And this means the limit does not exist. Make sure that you write the limit does not exist, or D&E. We need to talk about some terminology now, because we want to talk about what if we can't make a full delta ball around the point. So we want to talk about what are interior points, what are boundary points, in order to expand our definitions of continuity and differentiability. Let's talk about an interior point first. Let's suppose that we have the XY plane, or R2, and we take a subset of it that we call S. Let's suppose a point P0 is called an interior point of S. That happens if there is a delta disk centered around P0 that's contained completely in S. So in that case, you're going to have some region of R2 that is your subset or your set S. The point -1, 1 is an interior point because I can draw a delta ball, a circle of radius delta, all around that point, and every point inside that delta disk is inside of S. That makes that point an interior point. Notice the point 2, 3. 2, 3 is on the boundary of S. No matter how small I make delta, some of the points inside the delta disk are going to be outside of S, and some are going to be inside S. That makes it a boundary point. If it contains points both inside and outside. What about a connected set? What do we mean by a connected set? Again, we're going to start with a subset of the real plane, the R2 plane. An open set S is a connected set if it cannot be represented as the union of two or more disjoint, non-empty open subsets. What does that mean? All right, disjoint means they have nothing in common. There's no overlap between the two sets. Non-empty means each set has at least one point inside of it. Open means they are open. Now let's take a look. If it cannot be represented that way, what does it have to look like? Well, that set is connected, but this set is not. This set consists of two disjoint, non-empty subsets. They don't have any overlap, but they're both part of S. So they're separate, right? In this case, it's one thing, and you can get from any point inside of the set to any other point inside the set without leaving the set. That's what we mean by connected. What do we call a region? A set S is a region if it is open, connected, and not empty. So basically, this becomes a region, but when it consists of two disjoint sets, we don't call it a region. It actually consists of two regions, right? So it's not a single region. The definition of the limit of a function of two variables requires the delta disk to be contained inside the domain of the function. However, what if we want to find the limit of a function at a boundary point of the domain? Say the domain went from 0, 0 and included all of quadrant 1. Then the point 0, 4 is on the boundary. If we draw a ball, a circle, a delta disk around 0, 4, some of the points are inside quadrant 1 and some of the points are inside quadrant 2. In that case, it's a boundary point. How could we find the limit of a value of the function defined in quadrant 1 as it approaches that boundary value of 0, 4? We need to consider only points that are inside both the delta disk and in the domain of the function. In that case, in the half circle that lies within quadrant 1. Here's the definition for the limit of a function at a boundary point. It's very, very similar to what we saw for the limit of a function where it was an interior point. Suppose you have a function of two variables, x and y, and suppose that AB, the point you want to approach, is on the boundary of the domain. Then the limit of xy, the function, as xy approaches AB is L, and we write it in the normal notation. If for any epsilon greater than 0, there exists a delta greater than 0, such that for any point xy inside the domain of F, and within a suitably small distance inside the delta disk, then the value of the function is no more than epsilon away from L. And in symbols, we write it this way. And this right here, of course, represents the distance of the point, right? So again, what we're talking about in something like this case is we're talking about a function and here's my point 0.04. And the function xy has a domain which is equal to quadrant 1 plus the axes. Right? So it includes the x-axis, positive x-axis, positive y-axis, and the origin and quadrant 1. So it's defined, if you will, in this region right here. The problem is, if I draw any kind of delta disk around that, I have some points that are not inside the domain of the function. Then I can adjust the definition of the limit so that I only check the ones that lie both within the delta disk and within the domain of the function. Now that we've discussed limits at both interior points and boundary points, we're ready to talk about continuity. The definition of continuity for a multivariable function is very similar to the definition of continuity that we saw in Calculus 1. Let's go ahead and take a look at the definition of continuity that we see here. A function f of xy is continuous at the point a comma b if the limit as xy approaches that specified point ab of the multivariable function is equal to f of ab. Now, again, what is that implying? That is, the same three conditions we had in Calculus 1 still hold. The function exists at the ordered pair a comma b. The limit as xy approaches the ordered pair ab of the function exists. That means it's a finite real value along any possible path. The third condition is that the limit as xy approaches the ordered pair ab of the function is equal to the function value at that point. So we often combine the three conditions together by stating that the limit of the function is equal to the function's value at the point. That implies all three conditions. Let's take a look now at all of the different theorems that we have. All the standard functions that we knew to be continuous from Calculus 1, they're still continuous. Polynomials are still continuous, sine is still continuous, cosine is still continuous. All the ones we had before are still basically continuous. It's just that now we're substituting in more than one independent variable. We just need to watch out for the same things we needed to watch out for before. That would be division by 0, even roots of negative numbers, logarithms of 0 or negative numbers, and so forth. This means that if we have a continuous function and the point AB is not a point of discontinuity, then to find the limit value, all we have to do is substitute in the values. In other words, I'm now giving you the justification for the method we used to evaluate the limits earlier. This is much easier than those limit laws. Let's take a look at the sum of continuous functions. If you know that f as a function of x and y is continuous at some point x naught, y naught, and g of xy is also continuous at that same ordered pair x naught, y naught, then their sum is also continuous at x naught, y naught, and their difference as well. Let's take a look at the product of continuous functions. The product of continuous functions is the same as well. Now, in this case, g of x times h of y is going to be continuous at x naught, y naught. That is, if g of x is continuous at x naught and h of y is continuous at y naught, then f of xy equal to g of x times h of y, so it becomes a function of both x and y, is continuous at x naught, y naught. Now notice that in the definition of this function, we had two functions of one variable, one of x, and one of y. If each of those is continuous, then their product, which is a function of multiple variables, is also continuous. Now let's take a look at the composition of continuous functions. Let's suppose that g is a function of two variables, say x and y, from a domain that is a subset of the real plane, the xy plane, to a range that is a subset of the real plane. Remember, we're mapping ordered pairs xy to single finite real values, z values, which are on a number line, a real number line. Suppose that g is continuous at some point x naught, y naught in its domain, and we'll let z naught represent the z value at that point. Let's let f be a function of one variable that maps the reals to the reals, such that z naught is in the domain of f. So we're going to apply g first to the ordered pair, x naught, y naught, get a z naught value out. Then we're going to apply a function f to that z that came out. Let's suppose that f is continuous at z naught. Then the combination f composed with g is continuous at x naught, y naught. Let's take a look at what the picture of this situation looks like. The composition of two continuous functions where one is multivariable and one is single variable is continuous. We start with a subset of the real R2, the xy plane. We take an ordered pair under G to get a single finite real value z. This then maps under the function f to another real value. So G is a function of two variables, f is a function of one variable. And the composition is continuous at the value xy or x naught, y naught. Let's go ahead and take a look at example 4 now. In example 4, we want to show that the functions f of x and y given by 2x squared y cubed plus 3 and g as a function of both x and y given by 2x squared y cubed plus 3 quantity to the fourth are continuous everywhere. So it's more of a word type proof than anything else. We start by breaking it apart into its component functions. The term 2x squared y cubed can be split into a function of x, 2x squared, and a function of y, y cubed. I know from single variable calculus that 2x squared, being polynomial, is continuous everywhere, as is y cubed, also polynomial. In that case, by the rule above, the product of continuous functions theorem, 2x squared y cubed has to be continuous at every point xy in the xy plane. Since L of x equal to 3, which is just a boring horizontal line, is also a continuous function for all values of x, every real number, by the sum of continuous functions theorem, 2x squared y cubed plus 3 must be continuous at every point xy in the xy plane. Now we want to prove that g is continuous everywhere. Well, we've already proved that the interior is a continuous function. 2x squared y cubed plus 3 is continuous at every real ordered pair xy in the xy plane. However, we also know that the linear, or not linear, the single variable function x to the fourth power, being polynomial, is also continuous over the entire real number line, which means that if we compose x to the fourth with 2x squared y cubed plus 3, then by the theorem for the continuity of composition of functions, we know that it has to be continuous at every point in the xy plane. Let's now take a look at limits and continuity for functions of 3 variables. We can extend this as well to functions of 4 variables or 5 variables, but in multivariable calculus, we rarely go beyond 4 dimensions, a function of 3 variables. What we need to define in order to do this is we need to extend that idea of the delta disk, which was a circle in the xy plane, to have a delta sphere, or a delta ball, if you will, in 3 dimensions. If I have a function of 3 independent variables, say w equals a function of x, y, and z, then my domain is 3-dimensional space. So if I have a point in 3-dimensional space and I want to be the same distance away from it all the way around, then I'm talking about a sphere around that point, or what we'd call a delta sphere, or even a delta ball. Let's now take a look at the limit of a function of 3 or more variables. Now, this occurs quite a bit in applications. For example, you might have a function that gives the temperature at a physical location in 3-dimensional space. So W is the temperature, which depends on your location. Or perhaps it indicates air pressure at a particular location, or maybe at time. How can we take a limit at a point in R3? And what does it mean for it to be continuous at a point that is in 4 dimensions? 3 independent variables, 1 dependent. What we're going to do is we're going to extend the idea of the delta disk into a delta sphere, and then you'll see that the limit ideas and the continuity definition just naturally expand to multiple independent variables. We're going to start with an ordered triple, x naught, y naught, z naught, as some arbitrary point in 3-dimensional space, R3. Then a delta ball or a delta sphere in 3 dimensions consists of all the points in R3 that are less than delta away from that ordered triple, x naught, y naught, z naught. And we can give the distance with the square root of the partial equation of the sphere. And we can say that it has to be less than delta, where delta is some strictly positive value. To define a delta ball in higher dimensions, you just add additional terms under the radical, which may sound kind of crazy, but this one would be a delta, well, you can't call it a sphere. I don't know what you'd call it. But anyway, we're in 5-dimensional space because we now have a function of 4 independent variables, w, x, y, and z. Or it could be t, x, y, and z. So time, position, and maybe the output is temperature. All right, so we have something where the domain is R4, but the output gives us the additional dimension, so we're in R5. So you simply extend the formula by adding another binomial square under the radical. To show that a limit of a function of 3 variables exists at a point, it's good enough to show that for any point in the delta ball, the value of the function is arbitrarily close to the limit value, just as we did before. All the limit laws that held for 2 variables hold for functions of more than 2 variables as well. So if we're taking a look at example 5 here, the first thing we ought to try is to substitute it in. We know from continuity that if it's continuous there, the limit exists and it equals the value of the function. So if we can find that the limit is the value of the function, we've proven that the limit exists, the function exists, and the two are equal. So we've not only found the limit value, but proved it's continuous at the point as well. So the first thing we're going to do here on this one is we're going to go ahead and substitute in the values with a question mark because we don't know if we'll get a finite real. So this gives me 13, substituting 4 in place of x, substituting -1 in place of y, and substituting 3 in place of z. This will give me the square root of 13 minus 16 minus 2 plus 9 which gives me -5. I'm getting the square root of 4, which gives me 2. So hopefully that's what you got at home. If not, I may have a typo somewhere. But basically, I got a value, which means that the function exists there and the limit exists there, and they're the same, which means it's even continuous there. But I got the limit value. Let's take a look at the last example. Show that the function f of xy, 26 minus 2x squared minus y squared, is continuous at a point 2, -3. This is not actually a function of 3 variables, so I must have it in the wrong place. I'll get it moved. In this case, when we're looking at this one, we know from our limit laws that because x squared is a continuous function and 2x squared is a continuous function and -2x squared is a continuous function and -y squared is a continuous function and 26 is a continuous function, then their sum and difference is also continuous. Now, the outside function is the square root of x. And square root of x is defined for non-negative values. So long as 26 minus 2x squared minus y squared turns out to be greater than or equal to 0, then it should be defined. To show continuity at the point, we simply need to establish that it exists at the point. In that case, we can go ahead then and plug in our values. When we plug in the values for the ordered pair, we get that the function value at the point is 3. In other words, it is defined there. Because it's defined there and the limit of it would give us the same value, we know that it's continuous at that point. This is the end of this rather short section on limits and continuity. In the next section, we'll start our look at differentiability by defining what we mean by a partial derivative. I hope to see you for the next video in the series.